Hello everyone, this is Machine Learning for Earth System Modeling, Course 2. I'm Gabriel Moldovan, a machine learning scientist at ECNWF, and today I will be giving the Module 4, the Deterministic AI Forecasting System, AIFS-Single. So here's a list of the things we're going to explore. So we're going to have a look at what is exactly data-driven forecasting, how are data-driven models trained. We'll have a look at the architecture of the model of the AIFS-Single. Then we'll have a look at how skilled this model is and how useful, and then we'll draw some conclusions. So what is data-driven weather forecasting? You might be familiar with the conventional weather forecasting pipeline. We have initial conditions or analyses that are determined from the observing system and through the data simulation system. For the AIFS, is the data simulation system of the AIFS. We feed these initial conditions into a numerical model, and then we obtain a prediction of the state of the atmosphere. Right now, for data-driven weather forecasting, the pipeline is pretty similar. For the AIFS, we actually use the same initial conditions as the AIFS, so we use the data simulation system of the AIFS system. But we can have potentially more flexible data structures in the initial conditions, and also use maybe different temporal frequencies. But really what changes here is the numerical model. We swap the numerical model with a statistical model that is trained, that is learned using historical data. And then we produce a prediction as in conventional weather forecasting. Now let's move on to the training setup of the AIFS-Single. So there are some key design choices that one has to make, or that we made when we trained the AIFS-Single. And this is represented in this figure here. So first of all, which data goes into the training pipeline? So input and outputs. And this is very important because you could have targets that are not the same as the inputs. So this is really a design choice that the scientists, that the researchers have to make. What should the training task be? How am I going to produce the forecast? And also, very importantly, what should the loss function be? We'll not go into the model architecture for now, but these are the three core design choices that one has to make when training the AIFS model. So what variables should we use and which datasets? So there's two driving motivations: what helps me predict better and what the users want from the system. The typical set used by many models, such as GraphCast, the AIFS, etc., is 13 pressure levels. And on these different pressure levels, we'll have relative humidity, temperature, winds, and geopotential. And at the surface, you have key variables such as 2-meter temperature, mean sea level pressure, 10-meter winds, precipitation, etc. So which datasets I use for training the AIFS V2? We use ERA5 from 1979 till 2022. This is a consistent dataset, and it presents one of the most accurate and reliable and easy to access datasets of the previous state of the atmosphere for more than 40 years. And the years used for training are 1979 up to 2022. And then we also use operational analysis. Operational analysis is used for fine-tuning for two main reasons. One is that the AIFS uses the operational analysis for its initialization. And secondly, the operational analysis could be argued it has better accuracy than ERA5. So there is 2 points or 2 factors that can impact forecast skill on the AIFS, and this is why we train on operational analysis. Here is an exhaustive list of the variables used in training the second version of the AIFS. We have atmospheric state that is represented at 14 pressure levels. We have geopotential, horizontal winds, vertical wind component, temperature, specific humidity at all these levels. We have some external forcing, such as land sea mass, orography, time and geometry related variables such as latitude, longitude, insolation, time of the year, etc. And also we have some key surface variables such as surface temperature, near surface winds, precipitation related variables. And newly in the version 2 of the AIFS, we have ocean and wave related variables. And also we have some radiation related variables that are used for especially energy forecasting. So we know now what data we use for the for training the AIFS. We'll now move to the training task. So it's very important to define quite precisely what the training task of the model will be. So for the AIFS, the training task is the following. Given era 5 initial conditions, xt, so the state of the atmosphere at the time 0, at the time t, and also maybe past past states of the atmosphere, we want to learn a mapping from this state of the atmosphere into the future, so that the predicted state xt plus delta t, which is in AIFS 6 hours, approximates the true era 5 atmospheric state at t plus 6 hours. So we have a forecast that needs to be very close to the era 5 analysis. So this is the objective of the model and what it will be trained against. So this corresponds to learning a data-driven approximation of the atmospheric time evolution operator, learned really directly from reanalysis data. And then this forecast can be is then autoregressively stepped into the future. So the forecast becomes actually the initial conditions for the next forecast. So we can autoregressively um, and sequentially step into the future using this approach. Now we move to another very important point, which is another very important key design. So what loss should we optimize? So this is related to what should the model care about. In the case of the AIFS-Single, we use mean squared error loss. So mean squared error loss is robust and easy to implement, but it penalizes large errors quite strongly. So the model, we tend to take less risks in the forecast, and it will produce smooth fields. An alternative would be a probabilistic loss, which will be introduced in the next lecture when we will present the AIFS CRPS, so the probabilistic version of the AIFS. So probabilistic loss such as CRPS is harder to implement because it requires an ensemble, but it evaluates the full predictive distribution. And here is just a schematic representation of both losses, while in the mean squared error case, we're really focused on minimizing the forecast error. In the CRPS case, we want the cumulative distribution function to match the observation step CDF. And what minimizes the CRPS in the probabilistic case is having a well-calibrated ensemble, and this produces overall better results. But I'll let you explore this a little bit more in detail in the next lecture about the AIFS CRPS. For all the losses, for any losses that we choose, and in the case of the AIFS-Single in the mean squared, for the mean squared error loss, we have to decide on how to aggregate other variables and weights. So we need to decide what weights we add to geopotential, to temperature, to the surface variable. So, and this is also a key design aspect. Now, we can move on to talk a little bit more about the architecture of the AIFS-Single. So which model we chose here? So as you can see in the schematic, we have determined what data goes into our AIFS pipeline. We know what the training task should be, so we want the model to learn how to autoregressively step into the future using analysis data or reanalysis, and um, we have the target determined and also the loss function that we want to use, which is mean squared error. But now let's have a look at what actually is inside the architecture of the model. In terms of architecture choices, we have many options, or mainly four. We have convolutions, graph neural networks, transformers, Fourier neural operators, and the literature has explored all these different possibilities. But for the AFS, we have chose to use graph neural networks. So graph neural networks were first demonstrated by Keisler in 2022. In GNNs, data is structured in nodes and the connections between them. And the most popular one is the message passing GNN. So GNNs were further developed and demonstrated in GraphCast and used in early versions of the AFS. And later versions of the AFS introduced attention-based GNNs in the encoder and the decoder. Why GNNs were chosen for the AFS? One could argue that the main point is really the flexibility that we have in terms of data. They can really handle irregular data in space, and they don't present any issues at all. So let's have a more detailed look into the architecture of the AIFS-Single and really what's inside this model. So for the architecture of the model, we have to distinguish between two spaces, two data spaces. So first, we have the physical space, or the data space, that represents the state of the atmosphere and where the inputs and the prediction of the model live. So this prediction is represented in a grid at a resolution, in a reduced Gaussian grid at a resolution of roughly 30 kilometers. For the input, and at each node of this grid, we will have all the variables we mentioned before, plus and the forcing, of course, at the time t and at the time t minus 6. And in the forecast, at each node, we'll have the prediction of these variables at the time t plus 6. We then have a second space, which is the latent space that lives on a hidden mesh, in which the state of the atmosphere is represented in a learned latent form. This hidden mesh has a coarser spatial resolution when we compare it to the data grid, so it has roughly a resolution of 100 kilometers. But each node in this grid contains a high-dimensional feature vector. In the AIFS-Single, this latent representation uses a dimension of 1024 features per node. So when you compare it to the data space for each node here in the data space, we have around 100 variables. Now that we have the two data spaces clear, so we can move on to explaining a little bit how the model actually functions. So we use a graph neural network, which consists of three main components. So we have an encoder, a processor, and a decoder. So the encoder maps information from the data space to the latent space using cross attention, as you can see in this figure. So each latent node attends to each latent node in the hidden mesh attends to a number of nodes in the data space, producing a single latent representation per node in the hidden mesh. So this is repeated for all nodes in the latent space until we have a complete latent representation of the state of the atmosphere. So once all the latent space are encoded, the atmosphere is fully represented in this high-dimensional coarse latent space. And then the processor, the second part of the model, is used to advance the system in time. So this is done using attention. However, a node-to-all attention, so one node attending to all the nodes, and this happening to all the nodes, would become computationally quite prohibitive. So we need a better strategy for attention here. What one could do, and something we do in the AIFS v2, is we can use sliding window attention, where instead of each node attending to all the nodes in the hidden mesh, what we do is that each node attends to a band of nodes, to a longitudinal band of n nodes. And in the AIFS-Single, this number of nodes is 1,120. So this reduces the computational cost by quite a lot, while still maintaining quite a good forecast skill in the model. So you can see here the example of polar query node, where we have in red the node that we are attending, that we're really focusing on, and in blue we have the attention band that attends to this node. And here you have the example of an equatorial query node, and the same, you can see really the attention band that this node uses for attention. And again, this is much more computationally tractable than the previous example before, where the node would have had to attend to the whole globe. And finally, we have the third component of this model, the decoder, which also uses cross-attention between the latent nodes and the data output. So here we have 3 latent nodes that are used, and they attend to one single node in the data space or in the output. And once all the nodes in the data space are attended to, are determined, we have the final 6-hour forecast in the physical space. So now we move to the training loop. So the training loop consists of a forward pass through the GNN, just as we described before, starting from the data space into the hidden mesh with the encoder. We have the processor that determines the state of the system at t plus 6 hours in the latent space, and then we have the decoder that decodes back into the physical space, and we have the forecast in this space. We then compare this forecast against the target, which is either ERA5 or the operational analysis, and a mean squared error loss is computed. Through backpropagation, the model weights are updated, and this process is repeated over hundreds of thousands of training iteration times until we have a fully trained model. And the training scheme follows two-step procedure. So in the first step, we'll only use ERA5 data, and the input of the model is always ERA5, so we don't have rollout training in this phase here. So we only produce 6-hour forecasts using ERA5 data. But in the second step of the training, we use the operational AIFS analysis, because as I said before, in operational mode, the AIFS uses the operational AIFS analysis, so it's really helpful to train the model so that it sees the data distribution and the data distribution shift when comparing the AIFS analysis and ERA5. And in this second step, we also do a rollout. So in the second step, we forecast up to 72 hours. And as I said before, we start from analysis initial conditions, but once the first forecast is performed, we use this forecast as input for the next forecast up to 3 days, up to 72 hours. And we compute the mean squared error over all these different, over all these different steps. And then we backpropagate back into the model, and we update the model. So we optimize the model in order to produce up to 72-hour forecast. Now, let's talk a little bit about the AIFS-Single configuration. So the AIFS-Single um, V1 is operational since was operational since the 25th of February 2025, and the AIFS-Single V2 is operational since the 12th of May 2026 this year. The AIFS-Single, as I mentioned before, is started from the unperturbed initial conditions of the IFS ensemble control, and we produce 15-day forecasts at the resolution of N320, so at around 30 kilometer resolution with 6-hour hourly output. Now let's have a look at how skilled the AIFS-Single is, and for this we'll use a scorecard where we compare the IFS against the AIFS over 2024. So how this scorecard is computed. So first we compute several metrics such as anomaly, correlation, root mean square error, forecast activity, etc. against the IFS operational analysis and observations. And we compute these metrics for forecasts up to day 10. So in this scorecard, each square represents the metric at a single day. So we have 10 squares, which means that here we are reporting scores or metrics up till day 10. So we compute these metrics, error metrics or anomaly correlation metrics, and then these metrics are directly compared against one another. So we have the metrics for the AIFS and the metrics of the IFS compared against the same reference. So it is fair to actually compare them. So here we report scores for different variables, key variables in the atmosphere, such as geopotential, temperature, and winds. And in the upper block of this scorecard, we have the scores against the IFS analysis, and in the lower block, you have the scores against observation. We also compute scores for surface variables, key surface variables, such as 2-meter temperature, 10-meter winds, and precipitation, which uses a specific score, which is the SIPS score. So I would encourage you to maybe stop at this slide for a moment and have a look at the scorecard. Whenever it's blue, it means that the IFS scores better than the AIFS, and this is a scorecard for the whole of 2024. So in general, we see that we have better performance overall for the AIFS, but we have less forecast activity. Because as I said before, this model is trained using a mean squared error loss, which encourages smoothing in the outputs. We do see that we have some degradation in the stratosphere, the reds that you see in the scorecard, and the scores tends to be a little bit worse for show lead times, for example, 1 to 2 days, but this is only when we compare against analysis. When comparing against observations, the model is actually quite strong. So overall, the AIFS is quite skilled. So is the AIFS useful? And now I'd just like to present some case studies that show a little bit the strengths of the AIFS. The first case study that I'd like to present is a rare snow event along the Gulf Coast in the USA. And what is really interesting about this case is that this type of snow events did not happen at all, or is not present at all in the training dataset, neither in the operational IFS analysis nor the ERA5. So it's quite a rare event. And this is a really nice test case to see if the AFS can extrapolate and can produce a type of event that it has never seen. So this happened in January 2025. We had this very rare snow event along the Gulf Coast, and quite impressively, you can see here that the AFS managed to forecast quite quite skillfully this event even 10 days in advance, which is even better than the IFS model. So this is quite encouraging because this really shows that the model can really predict the type of events, extreme events that it has actually never seen before. And so a second test case I would like to show is heavy precipitation event in Queensland. Here we have huge precipitation totals that happens at the beginning of February in 2025 over this region. And even if this is quite an extreme event, the AIFS managed to forecast it quite uh, quite skillfully. When we compare IMERGE data here against the IFS, we see that the two main affected regions here, which are represented with two stars, are quite well, the event is quite well captured in the forecast overall. So this is overall quite encouraging because even though we know that the AIFS-Single struggles with extremes and it tends to underpredict them, the forecast can still be useful, and this is not a systematic issue in all the extremes. So this type of models can also be useful for forecasters. So a third case study I would like to present now is a spring event in France that happened the 30th of April 2025. We are showing here forecast data for Poitiers in France. So the 30th of April, more than 25 degrees were measured in Poitiers, and we can see here in this in the forecast reported here for different models that the AIFS model was the one that managed to capture or to forecast this event much more in advance than the other models. So this is really quite encouraging, and we also see that the AIFS model, which is presented here, the forecast over France is in general it's much closer to the analysis reference that we had for this day when we compare it against the conventional IFS forecast. So overall, we know that 2-meter temperature forecast is really one of the strong points of the AFS, and it really manages to score very well for this variable. So the forecast, 2-meter temperature forecast of the AFS are really skilled. And now, as a conclusion on this whole talk, so on the different aspects that we have seen on the AIFS-Single. So just as a reminder on everything, so the AIFS-Single is trained on ERA 5 for 40 more years, and also on the operational IFS analysis for duration of 8 years. Inputs at time t and t-6 for outputs at t+6. So we have a time step of t+6 hours. The loss function used to train the AIFS-Single is the mean squared error, but this produces smooth forecasts. The architecture used is graph neural network. It uses cross-attention for the encoder and the decoder, and a sliding window self-attention in the processor. We have two training phases. First training phase, pre-training phase, where we do t+6 forecasts and we only use ERA 5. And then we have a rollout fine-tuning phase where we use operational IFS analysis and we do forecasts up to 72 hours. The AIFS-Single is operational since February 2025 with forecasts of up to 15 days with 6-hour time steps. And I would like to also talk about a little bit what's really behind the IFS, which is Anemoi, which is an open source framework that was actually used for training the operational version of the AIFS. Anemoi provides a complete toolkit to develop data-driven weather models, from preparation training up till inference, and it is maintained and developed by ECMWF and some of its member states. And if you like some further reading, I'll leave you here to papers on the AIFS-Single. So we have the AIFS-ECMWF data-driven forecasting system, which was the first paper which describes the architecture of the AIFS-Single. And then we have a second paper, the AIFS-Single version 1, which describes a little bit the first operational version of the AIFS and some changes that that were implemented for this first version of the model. So thank you very much. I hope the lecture is useful, and you'll have some extra material on Jupyter Notebook, which I hope you will enjoy. Thank you very much.